NENOMATICA, where mathematics meets YouTube excellence. In this lesson, we will derive the alternative quadratic formula for the special case where the coefficient b is even. We will also define delta prime and use it to classify the roots into three cases. Start from the standard quadratic equation. Ax squared plus bx plus c equals 0. If b is even, write b equals 2b prime. Recall the usual quadratic formula. X equals negative b plus or minus the square root of b squared minus 4ac, all over 2a. Now substitute b equals 2b prime. Simplify inside the radical, that is 4b prime squared minus 4ac. Factor out 4, take its square root, and finally cancel a factor of 2 in numerator and denominator. Introduce delta prime. Delta prime equals b prime squared minus ac. Then the compact formula is x equals negative b prime plus or minus the square root of delta prime over a. We also compare the square root of delta prime over a. We also compare with the usual discriminate delta equals b squared minus 4ac, which here satisfies delta equals 4 times delta prime. Now, let's classify the roots using delta prime and visualize each case. When delta prime is positive, there are two distinct real roots. When delta prime is 0, there is one repeated real root. When delta prime is negative, there are no real roots, only a complex conjugate pair. Recap. When b is even, write b equals 2b prime. Define delta prime equals b prime squared minus ac, and use x equals negative b prime plus or minus square root of delta prime over a. The sign of delta equals the sign of delta prime, because delta equals 4 times delta prime. That is the alternative quadratic formula. Alternative quadratic formula. In this lesson, we will solve two quadratic equations using the b prime and delta prime method. We will follow the exact sequence of steps. Find b prime, compute delta prime, then apply the formula for the roots. Example. Our first equation is x squared plus 4x plus 3 equals 0. We will compute b prime, then delta prime, and finally the roots. Step 1. Compute b prime using the relation b equals 2 times b prime. Here b equals 4, so b prime equals 4 over 2, which is 2. Step 2. Compute delta prime. Delta prime equals b prime squared minus ac. Here it equals 1, and c equals 3. That gives 2 squared minus 1 times 3, which equals 1. Since delta prime is positive, there are two distinct real roots. Step 3. Use the root formula with b prime x equals negative b prime plus or minus the square root of delta prime, all over a. Substituting b prime equals 2 and delta prime equals 1 gives x equals negative 2 plus or minus 1. Therefore, the two roots are negative 3 and negative 1. To build intuition, place the roots on a simple number line. Example. Our second equation is x squared plus 2x plus 1 equals 0. Again, we compute b prime, then delta prime, and the roots. Step 1. Compute b prime. Since b equals 2, b prime equals 2 over 2, which is 1. Step 2. Compute delta prime. 1 squared minus 1 times 1 equals 0. A 0 discriminate means one repeated real root. Step 3. When delta prime is 0, the single root is negative b prime over a. That equals negative 1 over 1, which is negative 1. So both roots are negative 1. Place the repeated root at negative 1 on a number line. A repeated root on a number line. A repeated root touches the axis and turns around when graphed as a parabola. Summary. Using b prime equals b over 2 and delta prime equals b prime squared minus ac allows quick arithmetic and clean mental math. 4x squared plus 4x plus 3, we obtained roots negative 3 and negative 1. 4x squared plus 2x plus 1, we obtained the repeated root negative 1. Practice a few more examples with different values of a, b, and c to master the method. In this lesson, we'll solve a quadratic using the b prime method. Our example has a discriminant equal to 0, so we will get a double root. First, the example. Then we will write the problem clearly. Step 1. Identify the coefficients in standard form and compute b prime. Standard form is ax squared plus bx plus c equals 0. We define b prime as b over 2. For our equation, Equals 9, b equals 6, so b prime equals 3, and c equals 1. Step 2, compute delta prime. Delta prime equals b prime squared minus a times c. Plug in the values. 3 squared minus 9 times 1. That is 9 minus 9, which equals 0. A 0 delta prime means the quadratic has one repeated real root. Step 3, use the b prime root formula for the double root. When delta prime is 0, x1 equals x2 equals negative b prime over a. Substitute, negative 3 over 9 equals negative 1 over 3. That is our final answer. To build intuition, let's graph the quadratic and see where it touches the x-axis. We'll draw coordinate axes, and the parabola y equals 9x squared plus 6x plus 1. Notice it just touches the x-axis at x equals negative 1/3, confirming the double root. As a quick contrast, consider x squared plus 6x plus 37 equals 0. In this lesson, we will solve two quadratic equations step by step using the delta prime method. We will carefully follow the exact structure, compute delta prime, decide the number of real roots, and apply the quadratic formula with delta prime. Here are the two problems we will solve. First, square root 2x squared minus 2 square root 3x plus square root 2 equals 0. Second, open parenthesis m minus 2n close parenthesis times x squared minus 2m x plus m plus 2n equals 0, with n greater than 0. Plan. For a quadratic of the form ax squared plus 2b prime x plus c equals 0, we compute delta prime equals b prime squared minus ac. If delta prime is positive, there are two real solutions. Then the roots are x equals negative b prime plus or minus square root of delta prime all over a. Problem 1. First identify a, b prime, and c. Here, a equals square root 2, b prime equals negative square root 3, and c equals square root 2. Compute delta prime equals b prime squared minus ac. That equals 3 minus 2, which is 1, so delta prime is positive. Therefore, we use x equals negative b prime plus or minus square root of delta prime all over a. Substituting gives x equals square root 3 plus or minus 1 all over square root 2. That yields two real solutions. To build intuition, let's visualize the two solutions on a number line. The left root is approximately 0.518, and the right root is approximately 1.932. Problem 2. We will again follow the same structure. Start with the equation. Identify equals m minus 2n, b prime equals negative m, and c equals m plus 2n. Compute delta prime as b prime squared minus ac. That simplifies to 4n squared, which is positive. Apply x equals negative b prime plus or minus square root of delta prime all over a. The square root of 4n squared is the absolute value of 2n. Given n greater than 0, absolute 2n equals 2n, so the roots are x equals m plus or minus 2n over m minus 2n. One of the roots simplifies nicely to 1. Summary. Problem 1 has two real roots, square root 3 plus 1 over square root 2, and square root 3 minus 1 over square root 2. Problem 2 has two real roots, m plus 2n over m minus 2n, and 1, using the fact that n is positive. The key steps were to form delta prime, check its sign, and then apply the delta prime version of the quadratic formula. Example. We will analyze for which values of m the quadratic equation mx squared minus 2 times the quantity m minus 1 times x plus m plus 1 equals 0 has two real roots, one repeated root, or no real roots. We will use the discriminate shortcut delta prime equals b prime squared minus ac, where b prime equals b over 2. First, identify the coefficients. A equals m, b equals negative 2 times the quantity m minus 1, and c equals m plus 1. To avoid carrying the factor 4 in the discriminate, set b prime equal to b over 2. Then delta prime equals b prime squared minus ac, which is 1/4 of the usual discriminate. Now compute b prime. Now plug into delta prime. We have delta prime equals the quantity 1 minus m squared minus a times c, which is m times m plus 1. Expand and simplify carefully to get delta prime equals 1 minus 3m. Summary. For m less than 1/3, two distinct real roots. For m equal to 1/3, one repeated real root. For m greater than 1/3, no real roots. In this lesson, we will solve a parameter problem about double roots. We are given the quadratic equation. Left parenthesis m plus 3 right parenthesis x squared plus 2 times left parenthesis 3m plus 1 right parenthesis x plus left parenthesis m plus 3 right parenthesis equals 0. We will find all m values that make the equation have a repeated root, and then compute that repeated root. For a quadratic written as a x squared plus 2b prime x plus c, a repeated root happens exactly when delta prime equals b prime squared minus ac equals 0. Let's write that rule and map a, b prime, and c for our equation. Now substitute these into delta prime equals 0. We get left parenthesis 3m plus 1 right parenthesis squared minus left parenthesis m plus 3 right parenthesis times left parenthesis m plus 3 right parenthesis equals 0. Expanding gives 9m squared plus 6m plus 1 minus left parenthesis m squared plus 6m plus 9 right parenthesis equals 0. Combine like terms to get 8m squared minus 8 equals 0. So m squared equals 1. Hence m equals plus or minus 1. To find the repeated root, we use x naught equals negative b prime over a. Let's apply that for each m value. Case 1, m equals 1. Substitute to get x naught equals negative left parenthesis 3 times 1 plus 1 right parenthesis over left parenthesis 1 plus 3 right parenthesis equals negative 4 over 4 equals negative 1. Case 2, m equals negative 1. Then x naught equals negative left parenthesis 3 times negative 1 plus 1 right parenthesis over left parenthesis negative 1 plus 3 right parenthesis equals negative left parenthesis negative 2 right parenthesis over 2 equals 1. To build intuition, let's look at the graphs for each parameter value and watch the parabola just touch the x-axis at the repeated root. We draw one set of coordinate axes. For m equals 1, the parabola touches at x equals negative 1. For m equals negative 1, a new parabola touches at x equals 1. Final answer, m equals plus or minus 1. When m equals 1, the double root is negative 1. When m equals negative 1, the double root is positive 1. In this example, we will find exactly which natural numbers n make the sum of 4 consecutive squares divisible by 10. Example, let n be a natural number, for which n is the quantity a equal to n squared plus n plus 1 squared plus n plus 2 squared plus n plus 3 squared divisible by 10. Step 1. Expand each square using the binomial identity a plus b squared equals a squared plus 2a b plus b squared. Combine like terms. We get 4n squared plus 12n plus 14. Now factor out 2 to prepare a divisibility argument. Therefore, a will be divisible by 10 if and only if the factor 2n squared plus 6n plus 7 is divisible by 5. Let that factor equal 5k, where k is an integer. We now treat this as a quadratic in n. Using the reduced discriminate method, with a equal to 2 and b prime equal to 3, the reduced discriminate delta prime equals b prime squared minus ac. By the corresponding quadratic formula, n equals negative b prime plus or minus the square root of delta prime, all over a. For n to be a natural number, the square root must be an integer. Since 5 times 2k minus 1 must be a perfect square, write 2k minus 1 equals 5 times an odd square, namely 5 times the square of 2t plus 1. Taking the plus sign yields n equals 5t plus 1. That is, n is congruent to 1 modulo 5. Therefore, the original sum is divisible by 10 exactly when n leaves remainder 1 upon division by 5. Quick check. If n equals 1, a equals 1 plus 4 plus 9 plus 16, which is 30, a multiple of 10. If n equals 6, the sum is 230, again a multiple of 10. Answer, all n of the form 5t plus 1. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.